problems with packs, right? All right, so remember this thing here, problems interfacing with the hospital net system, okay? All right, now image display. Now, yeah, you created image digitally. Now you can send them out, big files, but now you have to send them out. So how? Now you need to think, where am I going to display them? Okay, because if your display monitors are not of good quality, what's the point of having the way you acquire the images, beautiful images you acquire? You have this huge band network capacity that you can send images now, but you have a lousy TV or a lousy screen. What's the point, right? And so, how are we going to display it? So, image display, hard copy display, okay? Images on film. Pretty much nobody's doing that anymore, at least not in this area, okay? If they wanted to, then you go through a laser printer. And laser printers can work with wet processor or dry processors. Okay, I'm not going to spend too much time on it. I'm just going to move through it.
Should we review it in the reading a lot too for this test?
Just concentrate on what I'm going to say.
Okay.
Okay, on this section. Okay. So laser printers, for the most part nowadays, if they still have a laser printer, okay, and hospitals might have one or two scattered somewhere, because sometimes, say a patient is going to another country, they don't know if they're going to be able to read digital images. So you give them images, you give them pictures, right? You give them plastic, like that, okay? And so what you do is you have your digital image and you make a copy, a laser copy, okay? And for the most part, since nobody's using, or most, at least large and medium-sized hospitals are not using any chemicals anymore, any chemical processing, so no wet processing. So you go with the dry processor. Okay, so you use, so I'll tell you how it works. Soft copy displays. Now the soft copy displays, how you can have flat screen monitors or you can have CRTs, okay? And still, I'll talk about CRTs, but nobody uses CRTs anymore. I mean, you guys remember the old CRTs, what they look like? The big white TVs. Big white TVs and heavy, because they had a tube, a huge glass tube inside, heavy, okay? But so for the most part, it will be flat screens, LCDs, which present many advantages. One of the first advantage that you see is their size, okay? So let's take a look. A little bit about laser printers. Introduced in 1983. They can display only at 8-bit grayscale. So even though your system is capable of acquiring at 32 or 16, this thing is not going to be able to display all those grayscales. But anyway, we can see them anyway, so it's not a big deal. All right, but when you talk about capacities and whatnot, this is not. You cannot display the 32-bit grayscale. That clear? Okay. All right, so how do they work? They need light sources for laser printers, very specific of what they use. Okay, you cannot just use any laser. So they can use infrared. Obviously, it's not a laser. They can use solid state diodes, which is heat, and they can use the helium neon, 633 nanometers. Okay. The 633 nanometers. This is the wavelength, okay, of the laser. For the solid state diode, 670 to 680, and for the infrared, 780 to 820 nanometers. Okay, the one that is really common is the helium neon. Okay, the other two are not too common anymore. They used to, but not anymore. Hospitals, they still have a laser printer. Is going to be this one. All right. Laser printer components. Okay, so you need obviously you will need a laser source. And I'll show you a picture in just a second. So just listen to me for now. Collimator lens or beam shaping optics, and I'll tell you what they do once I show you the picture. You have a modulator which controls control the intensity of the laser. Deflectometer shaping lenses. Okay. Sometimes you want to disperse how the laser is going. Okay. Cylindrical deflection mirror, which is connected to this. Unexposed film storage, a place where you're going to keep your unexposed films and then automatically move them when you need them. Remember, one thing to remember is that laser film is can be exposed by any visible light, so they need to be in total darkness. They need to be in a sealed storage, otherwise they get exposed. You need a mechanical transport. So this is basically what happens. So here's the source. Here's the laser gun, right here. You have a laser gun. Then you have a collimator lens, okay, that can help you concentrate, okay, the energy of the beam. You reflect it here. This is a beam modulator, so it can play, it can change some of the characteristics of the laser, and then from here through mirrors, through lenses, you can send it here through another lens, and here's a polygonal mirror. Okay, these are mirrors. This mirror, and this is a polygonal mirror. And the purpose of the polygonal mirror here is to, and along with the lenses here, their purpose is to spread the laser. Because the laser is going to be, is one thing that you observe with lasers. They do, like other light, they will do open up as they are moving out. They will diverge, but very slowly. For the most part, they go very straight. I mean, look at this. So if you look at this laser here, I mean, has it expanded? Man, I have shaky hands. Can you see it? Has it expanded a little bit compared to here now? So you see that the dot is smaller here than is what is there. So it expands, but it doesn't expand as much as visible light. Okay, and so what they need to do is they need to open it up so they can expose the film, so they can expose the whole field. Okay, and then you have another mirror here, and this is what reflects the light into the film. Make sense? Okay. A dry processor, heat-sensitive film. There's the thermally processed silver base emulsion. Okay, the silver behenate is a laser light creates latent image centers. Okay, and heat from the laser latent image will actually create the image on the frame. Shorter shelf life, more sensitive to heat and humidity than the other types. Okay, this is the film exposed to gallium arsenide laser. Okay, carbon particles adhere to areas of exposure. You know what? Just ignore this. Just ignore this whole section of the film, the specifics to the film. Ignore it. What I'm talking, yeah, all of this that I've been saying. Ignore it. Okay. The process of the film. I mean, you should know.
I'll study it later.
I'm not going to ask you on the test.
Yeah.
Okay. It's just we're moving away from it, just like what we did from chemical processing. Don't spend too much time. Yes. Okay. So this is important. Now the soft copy display. Okay. Allows manipulation. So what is it that you're, just so we don't have anyone telling me after the test that you didn't know that? Okay. So what are we eliminating?
The film,
Laser film.
laser
right?
films.
Laser film. That his section, the processing of the laser film. How the laser, how it exposed the film. That's important. All I'm eliminating is this. Is the carbon base, the printing of the actual film. Okay,
So I'm putting
right, this section. All right. Okay, let me show you.
Okay, 3 slides.
Okay, look. Look. That you need to know. Okay.
Wait a minute.
Let me see. No. You don't need to know that one.
No.
Rid of that one. Get rid of that one. That's it.
Okay. Just
3.
Just 3 slides.
Someone said 4 back there. 3, right? Don't add any more.
3.
So we're going 3. 3. No, 3.
Can I see yours so I can make sure I label it?
Yeah, of course.
All right. So soft copy display. So these are images that are going to be displayed on a screen monitor. Allows manipulation of the image without re-exposing the patient. What do we mean by that? You can change contrast and density. Okay, that's what it means. And a few more things that you can do that we have looked at when we were looking at CR and DR. Some of the characteristics we can do, some of the things that we can do, the post-processing of the image. Okay. Can be viewed in multiple locations, which is good, and 2 types of monitor. And see, the other thing that is nice about displaying it in like this, in soft copies like this, that every copy, okay, is the original, right? Every copy. With film, if you make copies of copies, those are copies, and they never have the same quality. Here, they're going to have, as long as the monitors are equally calibrated and they are of the same capacity, the images should look the same. Okay, and every image is the original image. So, 2 types of monitors: cathode ray tubes, the CRTs, and liquid crystal display flat panels. Okay, so let's start with the CRT. These are the old CRTs. Components: you have an electron gun, and then you have a phosphor screen. The phosphor screen is displayed here, and once you hear phosphor, what is it telling you? Phosphor? Light. Phosphor, light. Okay, it will create light. So what you have, sorry, I'm passing by there. So what you have here is you're going to have this phosphor screen, and then you have an electron gun. And the electron gun, got it? The electron gun is going like this. Sorry, you gotta do this. The electron gun is going like this, and like this, and is hitting the phosphor, the screen. And in the process of doing that, is creating this bits of light very rapidly, and that creates the picture. Okay, and however, this electron gun is going like this. Have you noticed that when you're watching, you are watching a movie, and in the movie, someone is watching a movie? You see this line going? Have you noticed that? That was a CRT. That's what they did. Why does it do that? Because the movie that you're watching is going faster than what the CRT is going. And also, if you really pay attention to the CRTs, you have to pay real attention. You can see that you can see things are going like this, like a light, like illuminating is going like this very quickly. And that's the image. Those are pictures that are being projected very quickly. Okay? Got the picture? When we do fluoro next year, I'll spend probably about half an hour talking about it, but for today, this is enough. All right, this is another look. It's a cross section of what you have with the old TVs, right?
Oh, yeah.
Yeah, that's what they were wide, right? And if you were back in the early 70s, you know, they had this big, they made out of wood, this nice, nice things. And my grandparents had nice, and you had speakers on the side. Don't remember that?
Yeah, I remember.
Oh, you do?
that.
Okay, good. Yeah. I still have a CRT at home. It works great. Yeah, I do. All right, so how is it work? Let's see. So here is showing you the gun, and here these are electrons, and the electrons are hitting this phosphorus screen, and then you're seeing light very quickly, and you're creating the picture. Okay. The monitor. It contains picture tube or cathode ray tube, controls the brightness and contrast of the image. Beam scanning for a standard TV. Okay, this is important. It's going to do, it has a total of, 525 lines. Okay, lines of what? The screen, when you look at it, look at me for a second. I'm gonna let you take a picture. Okay, you look at me. Okay, you have a screen, and then you have 525 lines like this. And so the gun is gonna go, it's gonna scan 525 lines in a raster mode. Okay, all right. So what it can do when it's going like that, it can show you 30 images, 30 frames scanned per second. 30 frames. So that's where you can see movement, okay? Because it's showing you 30 frames per second. It's very fast, guys. I mean, think about it. In 1 second, from now to now, 30 frames, very quickly, okay? And so that's where we can see motion. Okay. All right, so you have an oscillator, so it's going like this. And then it's going back and boom, fills the other lines. Okay, okay. You want movement? Okay, there we go, movement. There you go. Take it now.
Oh, there we go.
Oh,
Yeah.
I didn't get it.
Yeah.
You get it?
No, it's
Oh,
okay.
yeah,
I
I
got
got
it
it.
before then.
Movement. Fine.
All right. Okay, so TV image quality. TV image made out of thousands of tiny little dots. And these dots, when they are hit with the electrons, they create a light, right? Dots are arranged into horizontal scan lines. So you have this frame, just like I showed you with that picture here. You have those lines, you have these dots. And those dots are hit with the electrons, and then they shine. Okay? Image quality is determined by the horizontal resolution and by the vertical resolution. Okay? And you have contrast, brightness, and lag. Okay? Okay? Lag is when it's going too slow. Okay? All right, LCD flat panels. They work different. What you have here, these are light sources. The light source shines on the individual pixel. So you have a current running through it, and then it shines. Let me play a short video here, ready for you, so you guys can. Okay, I'll get it from your. Take a look. This is from your. It's one of your tutorials from Web Access. Look at LCD. Oh, yeah. It's the same guy who showed the other day. He's pretty good.
This monitor uses liquid crystals to display images. How this thing works amazes me. Let me show you. Let's start at the back of the screen. If you look here, you'll see a row of LED lights at the bottom called the backlight. These are the only lights in the monitor. Next, I'll put in what's called the optical system, which makes the light even across the back of the screen. Now, the first sheet makes a nice, even white background for the light. The next piece is called a light guide plate. You can see it's covered with dots. When light enters from the bottom edge, it propagates down the plate by total internal reflection, unless it hits one of the dots. And they make some of the light rays emerge out of the front. Then engineers place a diffuser film. It helps to eliminate the dot pattern from the light guide plate. Then comes a prism film. You can notice here that where I have the sheet, it's much brighter than where it isn't. So at this point, if we put the last diffuser film on, we have a very evenly lit surface, all from the single row of LED lights at the bottom. The backlights are always on, but what controls what we see is this piece of glass. It functions as a shutter. At the back and front of the sheet are two polarizers. They stick tightly to the piece of glass, but let me illustrate it with two sheets that I have. If I lay this sheet on the optical system, you can see that it passes light. And if I put this piece on top, it also allows light to pass. But if I rotate it exactly 90 degrees to the bottom sheet, you'll see the light disappears. The bottom sheet creates polarized light, which will only pass through another polarizer set to the right angle. Now, of course, in this LCD monitor, the front polarizer doesn't rotate. Other than the on-off switch, the monitor has no moving parts. Instead, what we do is we place these two polarizers 90 degrees to each other, this configuration that allows no light through. And then, if we want light to pass, we twist the light within the glass pane to match the front polarizer. How? Well, it's a simple-looking piece of glass that does all the magic. Let me put it back on, and you can see that the image reappears. I just love that. It's actually a sandwich of glass. Engineers fill the space between the panes with tiny glass beads to keep them separated, and with organic molecules known as liquid crystals. The crystals have interesting properties in that they do not allow light to pass uniformly along both axes. Grooves are formed on the surface of both pieces of glass at 90 degrees to each other. The molecules in between line up in a beautiful helix. When light from the backlight passes through the first polarizer and enters the sandwich, it's rotated by the liquid crystal so as to allow it to pass through the second polarizer and emerge out the front of the screen. This is known as the normally white mode. Applying an electric field across a sandwich causes the crystals to line up lengthwise. Now the light that passes through the front polarizer is not rotated by the crystals and can no longer pass through the front of the screen. We call this the normally black mode. Now that we can control the light through the glass, how do we get color? Let's look in detail at the piece of glass. By controlling the voltage between these transparent electrodes, we can control the intensity of the light that passes through. Now, there's much more to the glass plate. Let's examine this section where my sleeve meets the gold background. If we zoom in, you can see it's made of pixels. If I turn off the image and backlight the glass sandwich, you can see the screen contains red, green, and blue sections. These are subpixels. The three together make a single pixel. In the sandwich, they are simply colored tiles that overlay the front transparent electrodes. They follow the RGB color model. We adjust the electrode shutter behind the subpixels so that they make up a particular color. For example, to get the color of the blue in my shirt, we set the red subpixel to 12% of maximum intensity, green to 21%, and blue to about 50%. And now for the last critical piece in the glass sandwich. On the back pane, engineers paint tiny devices called thin film transistors. That's why these monitors are often labeled TFT.
yes.
Each subpixel has a transistor which controls it. This transistor you see here functions as a switch that allows the screen to be updated row by row. By applying a voltage to a specific row while keeping the other rows grounded, we allow each subpixel in that row to receive video data coming from the top of the screen. Only one row can receive information at a time, but the speed with which this happens for each row is so fast that your brain blends it into a fluid image. What an amazing device, and also the technology that allowed computing to go mobile. Imagine laptops, cell phones, and tablets without lightweight screens. I'm Bill Hammock, the engineer guy.
Very cool, huh?
Mm-hmm.
Yeah. Yes, Chrissy.
Could you
Stretch it.
maybe post some answers to that quiz before our test on Friday?
What is it?
The quiz for 4:30? Just so we answer
I will.
before. Study.
Yeah. Let's see, where is
That's the one I
So
want.
weird.
In our slides. It is?
We're not finished.
No, it's not. You have to write
Yeah,
out.
you got it right now.
We should have a quiz on Friday. Test on.
Yeah.
Test when we come back. Yes.
I don't know what happened. You can see the squares now.
Shower, we get dressed, and we won't be in the same car, and then we have to take more of the charge.
Cannot see it. What happened? Oh.
We have a couple of slides on it. That would be cool.
Yes.
But then how much time for class? Still make it down.
Per person.
All right.
have to pay the parking lot part? You don't? Some parts. Oh, okay.
We're gonna leave early, and at least now, I really start to.
I'll get back by at least by 4:30. So. But yeah, probably get to it.
No more, I have 7 more slides to go through.
Okay, quiz on Friday.
All right, tell you what, since I
Quiz
I'm
on
not sure you're done, we'll be quiz on Friday, okay? And your exam will be when you come back.
Thank you.